today's topic is GPU top trumps. That's what I call it, because that's what I've been reminded of. You know, these in German it's called supertrump or quartet, where you have like these car top trumps where you say my car accelerates faster, and then another person says, yeah, but mine is heavier or whatever. And then you need to pick a category, and then if your card wins, you get both cards, and that way you try to trade cards. I've mocked this up as this game doesn't exist. Yeah, it's only in my imagination. I only have those 3 cards, even though I pretend with the serial numbering that there are more cards. There aren't. But I've mocked it up a little bit just for fun, what the categories could be. And actually, I think, at least for these 3 cards, the game would actually be kind of balanced, because for every category, you would be able to beat the other cards, at least somewhat. For example, with the A100, you could beat everyone in the bandwidth category. But then again, on the other hand, you could, for example, in the, what is it? Does the Intel GPU lose in everything? Ooh, that looks bad. Yeah, I think it loses in everything to the AMD GPU. Okay, too bad. But there's always a card that sucks. I guess that's how it is. Okay, but we're going to fun aside. These are some of the categories. I have in here the DRAM capacity, clock frequencies, bandwidth, and then a bunch of floating point execution rates. First of all, and these differ for all of the GPUs. All of the GPUs have a somewhat similar structure. That's what the GPUs kind of converge to. This is an NVIDIA marketing graph. We have like this big image in the background, you know, this thing around here, which kind of should show it's a schematic of the whole chip. And then you see a lot of these repetitive structures, these subunits called SMs, or streaming multiprocessors in NVIDIA speech, all centered around like this large level 2 cache here in the middle. And then it's probably too small to see properly. There's here around the edges, there are these HBM interfaces, the memory chip, interfaces to the memory chip, to move data from and to memory. And a breakdown of one of these SMs shows a bunch of execution units. And here, the number of execution units that each of the vendors put into their, each of these units, differs a little bit. They all have very similar numbers the numbers of these SMs don't differ too much, but the number of execution units they put in, they differ somewhat. Not too different. This is another marketing thing, this time from AMD, just to show the balance. Yeah, you see again, lots of repetitive structures. And if you zoom in on these, then that's definitely too small for you to see. There's a bunch of units that do stuff. What do these units do, and why are there different units at all? Because we need to differentiate a bunch of things, and this depends very much on the applications. The thing here is in floating point number formats that there is different kinds of floating point operations depending on what precision, with what precision they operate. The big thing that GPUs traditionally do very well is the top one, single precision, 32-bit single precision, or FP32. Computer graphics usually just use FP32. After a while, they standardize on that because that works well. And this is what GPUs traditionally do very well. For the traditional HPC market, single precision is not quite enough. People want, either because they're too lazy to think about whether less precision also works, but they just standardized on double precision. This is the format on the bottom. And I have these bars, a bit of a kind of a representation of the size of how many bits I allocated for each one of the mantissa exponent, and then one sign bit. You can see double precision. Well, yeah, it's double as wide as single precision. Makes sense, I guess. So most traditional HPC applications, double precision. For HPC applications, there are a bunch of HPC applications that use single precision very well. Among them, I think for us, it's mostly MD. MD is fine with single precision, I guess, because it's so chaotic that pretty much everything diverges very quickly anyway. and then it's only statistics. So I guess the full precision doesn't make much sense anyway. I think lattice Boltzmann also works somewhat well with reduced precision. And like I've said, computer graphics use them a lot. And where in the recent years, all these precision things have really come to place, all these even smaller precision formats. The oldest one of them is FP16 or half precision. And then there's formats like TF32, as NVIDIA calls it, which is, I think it's cheating because nothing in TF32 is 32. It's actually only 19, if I count correctly. They use the same exponent as the 8 bits exponent of single precision, but then just chop off some digits of the mantissa. I think that way it's very easy to convert. If you want to convert from TF32 to single precision, you just pad with zeros, and if you the other way around, you chop off some digits. So I guess that's they have other, except the aside the precision aside, they have similar properties, I guess. And then there's stuff like B float 16. I think the B stands for brain float. I don't know who comes up with these kind of names, and they shift around I think they put a few more digits toward the exponent because they think we don't need that much precision. Having a large range is more important. I guess that is better for machine learning. Yeah, all these formats mainly used in the training of neural networks. I have left out stuff like even smaller precision. FP8 is something that people do. Integer 8, integer 4 sometimes. But that's a point where that's really only usable for inference. For training a network, you really need at least something like FP16, because there you have a lot of weights and you change them very slightly. You need to compute a new gradient, and the change is very small. Otherwise, I guess it becomes unstable. And because this change is so small and you need to accumulate over a lot of small contributions, you need at least a certain precision for those contributions to actually make a difference. So for training, somewhat higher precisions. For inference, I think everything goes like as an integer 4, but that's not what I'm going to talk about today. Okay, now I have a table. Sorry, one more thing. There's also, like I've said, floating point operations are not made equal. Like I've said, there's different number formats, but there's also some of these numbers and execution units they have in there are not as flexible as other execution units. What NVIDIA introduced are those tensor cores that do small matrix multiplications. And this is in hardware, that's a very nice thing because you can save, I think, mostly on register bandwidth, because you can reuse a lot of stuff and need to move less data around, because these days in chips, you spend more energy moving data around than doing actual computation. So it's more efficient to implement a full matrix multiplication than implementing the same number of vector floating point operations per cycle. And but those floating point operations are only really useful if you have a problem that maps to these kinds of small matrix multiplications. That works very well for neural networks. Well, very often you have these kind of small matrix multiplications. It also works for, well, matrix multiplications, of course. The most known one is the LIMPAC. And for the HPC GPUs, the tensor cores, for example, in the A100 or the H100, they are actually FP64 capable, and then they deliver double the throughput. For the consumer GPUs, they don't put that in because it's wasted. But the bigger GPUs, the HPC GPUs, can actually use the matrix cores or tensor cores or whatever they are called for the LIMPAC. Yeah, so for matrix multiplications, that's nice. I think matrix multiplications in HPC are actually not the norm, or somewhat of an exception, or only a few problems really map to a pure precision matrix multiplication. So in the rest of this talk, I'm going to count vector FP64, vector FP32, and tensor core or matrix core reduced precision, because that works for machine learning. And so now I have a table with a bunch of GPUs, so many of which we actually do have here in our computing center. The RTX 380 is in tiny GPU, I think a few of them. The NVIDIA A40 is a big part of Alex. Those two GPUs are actually somewhat similar because they use the same chip, the same silicon, but the A40 has many more units enabled. In the RTX 380, there's a lot of disabled units. And also that's an actual consumer gaming product that you put into your computer, plug your display into, opposed to the A40, which is a server-only product. Then we have the NVIDIA A100, which is also a big part of Alex, which is the HPC-focused counterpart to the A40, and an NVIDIA H100 of the Hopper generation, the next generation. I have to say something about the versions, because both of the A100 and the H100, there's several different versions around. In Alex, we have an SXM4 version. That is a version where that we saw right here at the beginning. You have these kind of boards, and these boards plug directly onto the main board. Yeah, it's not like in the past, a graphics card that you put into your computer in the PCI Express slot. But these are much more integrated, so this works differently these days. So for the A100, we have this SXM version, specifically the 80 GB version. For the NVIDIA H100, so far we've had only access to the PCI Express version, and the PCI Express version is slower than the SXM version in a number of things, mostly the power budget. And with the reduced power budget comes reduced clocks and a smaller unit count. In this case, actually also less memory bandwidth. So if we compare now, for example, the A100 to the H100, in this case, it's not quite a fair comparison because the A100 that we have is like the high-end variant, and the H100 that we have access to is a low-end variant. So some of the progress, the generational progress, looks smaller here than it actually is or should be. Then we have two AMD graphics cards. The MI210 is the chip that powers the currently fastest supercomputer in the top 500 list. In this case, it's also, although the one that is in Frontier is a special version, a bigger version of that one, where they combine two of these chips into one GPU, and we only have the smaller version. So again, for the MI210, we have the small version. And then on the very right, we have two Intel GPUs. The Max 1100 we actually have here. This is, and this again is roughly a half version of the Max 1550, which we don't have access to yet. Okay, so getting that out of the way. Yeah, there's a question.
Are those now specs from the docs, or did you measure?
Those are specs. Yeah. Those are specs. I did not measure those rates because those rates are actually, you can, if you have an application that would be made the right way, you can probably get pretty close to the max rate. Sometimes there's limits, like I think for the RTX 3080, if you mix, you need the right instruction mix to really get that rate. But well, rarely is the peak rate here really the actual limiter. So here that's values that I just looked up on the internet. Yeah, in the FP16 domain, we can see for the NVIDIA GPUs, there's a generational large increase. So NVIDIA has invested for every generation, they've invested quite a bit of new silicon to make that faster. And I think they doubled the throughput from A40 to A100 to H100. The throughput per core with every generation, and then with a little bit of clock increases and unit count increases, then we get quite large increases in those throughputs. The other GPUs, the AMD GPUs, they haven't put that much focus on the machine learning things yet. That's probably going to change because everyone wants a piece of not just of our cake, but of the AI cake too. Yeah, and we see for the Intel GPUs, they have gone all in. They have the highest value with those 840. Yeah, so they can pretty much tie with the H100. For the vector compute, so single precision FP32 compute. I think the differences are smaller. Yeah, we even see a slight degradation that the A100 has slightly less. Has reasons that I won't explain right now. And for 64-bit, for double precision, there's one big difference. The two leftmost GPUs, those are not typos. They're really that little. It's only half a teraflops, where other GPUs do put out something like 50 teraflops. That's because they're consumer GPUs and they have a very, very low double precision throughput on purpose because gaming doesn't need it. For comparison, I've also put in the TDPs, the power consumption values. These are spec values. How much power the GPUs actually need can vary. And also, I wanted to put it in because the Intel GPU on the very right, it looks like, I mean, it takes the crown in every single discipline. It looks like the absolute champion here, but you can also see that it uses up to double the power of some of the GPUs. So I guess how good it really is remains to be seen. We also don't have one, so yeah.
I think also based on the specs, I think in terms of energy efficiency is slightly, but only slightly better than the top AMD model, which was the top candidate.
But based on specs, you said, right?
Just specs, based on specs. Of course.
Yeah. What is slightly open and what I really don't know is which GPUs can actually keep up their clocks if you really fully use some of the units. It might be that some of them drop the clocks a bit and then to keep their TDP. And also this chip here on the right, it's massive. It's a massively big chip. So could have probably also put in like area to have like an area efficiency or something. Other chips like the MI210, for example, are pretty small. And the 840 and the RTX 380 are pretty small chips. Okay. Yep.
Like I don't know that much about GPUs, so maybe that's a stupid question, but what's like the technical reason why I don't have this simple, I can do twice as many SP clocks than DP clocks? And for example, like why didn't Intel do that if they like went all in? If I already have a 64-bit register, why not just do them?
Yeah. I think for the good question, why is the usual ratio 1 to 2? I think you can, for additions, it makes sense. You can reuse some of the circuitry that you use for FP64 to do twice as many FP32 operations. That's actually not true for multiplications where you need 4 times as much circuitry. I think data path is very often just doubled, and that way double rate just makes sense. I think double rate is the technically most simple thing. Why, for example, the Intel GPUs have equal rate of double precision and single precision, I don't quite know.
I think that I'm not sure.
Yeah.
No less than you probably, but this thing is the core is based on the internal embedded GPU. It's the same core than in the previous generation embedded GPU. And I think the internal architecture is using SIMD. It's SIMD with 1 kilobit word width. And so therefore, when you have the same register, well, then double precision.
But you would fit double as many values in the same register size. Yeah. I don't know. I guess it could be an instruction throughput thing. For example, on the AMD side, they've doubled their FP64 throughput from the MI100 to the MI210, so that single cycle throughput, and they have now they have SIMD2 throughput for the FP32. So you need to pack two FP32 values to actually get the 46 teraflops for single precision MI210. So they increased that number and came up with a trick to actually make it usable for single precision. Yeah. Okay, but I guess enough of that. The other big part, except for computation, is bandwidth. Memory bandwidth is the biggest one. We have on the top here, on the top line here, the spec number, the theoretical width of the interface of the memory interface. And right below the second row is a number I measured. I haven't measured numbers for all the GPUs. The bars here for the first two rows are actually have the same scaling, so you can kind of see, for example, here for the A100, you get 1732 gigabyte out of 2039. There's always a bit of a certain efficiency involved in how much of the bandwidth you can actually get, and you could compute the ratio here, which kind of what kind of efficiency is that is. Some GPUs have worse efficiency than others. I think, for example, here the max 1100, that would only be something like 2/3 efficiency. On the other hand, you have here the A40, which gets 655 out of 696, which is, I guess, something like 95% efficiency. So those numbers always vary a bit. Something else I've measured, what we can see, the two gaming GPUs, less bandwidth because you don't need as much for gaming. The two HPC GPUs, A100 and H100, they have the same bandwidth because the PCI Express version of the H100 doesn't have as much. The SXM version, I think, goes up to 3 terabyte. How much of that it actually can realize, I'm not sure. And then, sorry, one too far. And then the others, they're in similar ranges, I guess. And how much the max 1550, how much of those 3.3 terabytes can realize, we don't know. Probably only something like 2 terabytes if we look at the numbers from the smaller version, from the max 1100. So probably won't even be that much faster than the other GPUs in actual realized bandwidth. One of the things I've measured is the level 2 cache bandwidth, just as a data point, as an interesting data point where you see a very clear generational improvement from the A40, A100, H100, and other GPUs in similar ranges. Let's keep it to that. The cache values, how much cache the L2 cache these GPUs have, and I'm actually talking about this because I think it's somewhat relevant for the next benchmarks that I show, or could be relevant. There's a split. Some of the GPUs have only in the range of 5 or 6 or 8 megabytes of level 2 cache, and that used to be the traditional value for computer graphics. Where you get good reuse out of textures and 3D models and stuff. And the A100 and the H100 has increased that quite a bit with 40 and 50 megabytes. And the Intel GPUs, they go really all out, and they even call this their Rambo cache, where they have 104 and 408 megabytes of cache. And this suddenly opens some possibilities that weren't possible before. And yeah, I think DRAM size is not so interesting. Gaming GPUs have less DRAM because there it's not important. Others have bigger more DRAM.
A question in the chat.
Yes.
What's the architectural reason for the difference in measured and spec DRAM bandwidth?
That's a good question that I really don't know. There's a memory controller, that gets tons of requests. And I think it tries to batch as many requests to the same memory page together because that makes things faster. And there's a trade-off, like, does it wait longer for more requests to come in, or does it process them quicker and then get lower latency, but also less throughput? So there's tuning involved in the memory controller, and the theoretical rate is really only the electrical interface width. So, and the other one is how many actually useful transactions can we actually get through? And it's also an interesting question if we do accesses that are not as regular as the ones what I've measured here, where I iterate through an array in linear fashion. Then in many cases, the bandwidth does drop even more. And I have seen that, for example, the AMD GPUs are less robust in the memory bandwidth, and that the achievable memory bandwidth drops quicker than on the NVIDIA GPUs. Why that is, I really don't know. Okay, now I have one more application where we have measurement benchmarks to compare. These are Gromix benchmarks from Anna Kala, which she has measured and which she has generously shared. They might have actually been shown here in the HPC Cafe before. I'm not 100% sure about those. We have 6 different systems. Those vary in size. I think they increase in size with from 1 to 6. And yeah, an observation we can make: the H100 is always the fastest GPU. First observation. And then we can see that the percentage of the smaller GPUs like the A100, the A40, and the RTX 3080, it decreases as the systems get bigger. Do they get slower because the systems get bigger? Well, yes, they do, because the numbers get smaller. Yes, but I think it's mostly that the bigger the GPU is, the more difficult it is to actually fully utilize the GPU. And we can try, of course, to correlate some of the numbers that are on the top, for example, the single position rate or memory bandwidth, and try to correlate them with the resulting performance. I think one thing that's pretty clear is that it doesn't correlate at all with the DRAM bandwidth, because we have very little DRAM bandwidth for the 2 leftmost GPUs. And then the A100 and the H100 have the same DRAM bandwidth, but the differences aren't that big. They're nowhere near in the range of the DRAM bandwidth. This is not that surprising, because molecular dynamics is usually not, or at least these GROMITS benchmarks, and it shouldn't be memory bound. Instead, the dataset sizes here, I think one of the system has in the range of 500,000 atoms, and I don't quite know what the others have. And I estimate that the data footprint of those systems ranges from somewhere between 5 megabyte and 500 megabyte. So, and that clearly spans those L2 cache sizes. So some of the bigger GPUs, one could think that they would fare better in those things. But there again, can we really cluster according to the L2 cache sizes? No, we can't. It's really not that clear. The speed up from the smallest GPU to the biggest GPU, it isn't actually that large. And that's where other things come into, like there's still CPU work being done that I actually don't quite know the details about, that just limits the scaling, the amount of scaling that you can see. And I think for the GPUs that get relatively slower with increasing system sizes, those are the smaller GPUs that are already somewhat fully utilized, even for the smaller ones. And the ones that get faster are the ones that need more parallelism or have higher latencies or higher startup overheads or whatever, to really get fast. This is especially true, I think, for the 2 AMD GPUs that actually get relatively faster when the systems get bigger, even compared to the very big H100 GPU. And I have one last slide, where I try to measure this overhead, this startup overhead. And this is a streaming kernel where I just copy data from one array to the other for 2 of the GPUs, the MI210, the AMD GPUs, and the V100 and slightly older NVIDIA GPU. I chose that one because they are in a similar ballparks in terms of speed. And then we have the grid size, or the array sizes, on the x-axis. And we can see for very small grid sizes, the startup overhead is so large that the startup overhead takes much longer than anything else, so the performance is very low. And as we increase the grid sizes, then we have this ramp up effect. And I actually have this fitted red line here that tries to model this as a very simple startup time plus bandwidth. And I fit something like 5 microseconds or 10 microseconds. And especially for the smaller systems, like the top one here, system 1, I think we estimated the time for one time step to be in the hundreds of microseconds. But that, of course, involves a lot of steps, a lot of different kernels, and also maybe some synchronization with the CPU. So one could imagine, or probably the time for each single kernel is in that range of the startup overhead. So probably plays a significant role. And in this kernel, we can see that the V100, the NVIDIA GPU, it ramps up much quicker for small grid sizes, even though in the end, for very large grid sizes, the AMD GPU, the MI210 is faster. It ultimately has the higher memory bandwidth, but for the smaller grid sizes, its large startup overhead just is too slow and hinders it.
Is this rooted in this difference in startup overhead? Is it a hardware problem or a software issue?
That's an interesting question. I'm not sure. I think it's both. I think it's both. One thing certainly is the software layer and how it handles, like initiating a kernel launch. Another thing is probably spreading work to the actual execution units. Another thing is how long does a single thread take from start to finish? And the longer that time is, the longer it takes for the very last thread to finish executing, and everyone else has to wait for the very last thread. So I think it's both. And for the V100, you can actually also see that there's a very clear L2 cache. You can see a bump here, or a peak rather, where we compute out of level 2 cache. For the MI210, there is something like a bump, but the startup overhead, the ramp up is so slow that it doesn't profit at all. Yeah.
Do you have some preliminary data for the input GPU as well? How?
Yes, I do. It does look, I don't remember the values, but I think the V100 is pretty quick with those. I have a fitted value here that fits to 3,000 cycles startup overhead. I think some of the bigger GPUs go at 5,000. Maybe the Intel CPU was in the range of 7,000 cycles. I think something like that.
Because with this bigger cache, you should clearly see this.
Yeah. The bump is very clearly visible for the Intel GPU. Yeah. Okay. So far to the GPUs of today that we actually do have. There's one very quick outlook, about the APUs, which is a future development. Both AMD and Intel, both AMD and NVIDIA are doing this. Intel has, I think, a few months ago said they wanted to, but they canceled a product that they had planned where they wanted to integrate the CPU cores and GPU cores, but now they said, yeah, not yet. They're not there yet. But on the right side, we have AMD. They're very actively doing this, and I think this is an annotated die shot of the MI300. Which I think, which you probably can't buy, but it's probably already shipping or sampling or whatever. I don't know what the state is. But here you can see these, 3 quadrants here contain GPU dies. And then on the lower right here, there is a bunch of CPU dies. And now you have both on the same die or on the same package sharing the same memory chip. So working on the same memory. This is quite useful because now you don't have to copy data between the GPU memory and the CPU memory, which so far are distinct memory structures. And that way coupling and I think for grommix, for example, I'm not a grommix expert, but I have heard that it still does a lot of stuff. Some of the kernels still run on the CPU. And especially if we have this very fine-grained sharing and switching between CPU and GPU, that would be quite could be useful. Of course, people have programmed around this limitation of separate CPU and GPU pools for the last 15 years and have gotten pretty good at getting rid of that fact. But especially for new ports, there's a lot less work to actually get speed out of the CPU. Now on the left-hand side, we have the Grace Hopper project with a Grace CPU ARM CPU, and on the right, a Hopper GPU. They don't share the exact same memory. So there's here up here, there is LPDDR DRAM chips. And then around the GPU, there are these HBM chips, but they're connected with a rather fast interconnect, 900 gigabytes per second. I think the interconnect is for the CPU, the interconnect is as fast as its own memory bandwidth. So the idea is the CPU can work on the GPU memory pretty much as fast, probably, as on its own memory. So it looks kind of as if they had the same memory, or it doesn't hurt as much that it's a separate memory space. So they're actually technologically, the AMD approach is cooler or more advanced. But NVIDIA should get a lot of the benefits of that too.
Question in the chat. What distinguishes APUs from many-core processors?
So APUs were, the term APU was made up in the beginning when AMD bought ATI. So they bought a graphics card manufacturer, and then they wanted to include GPUs onto a CPU die, and then they said it's really nice because now it's not just a CPU, now it's an accelerated processing unit. And they envisioned this future where a lot of things like Excel spreadsheet processing and JPEG compression and sound and whatever would be done by the GPU. This vision never really materialized, also because AMD just didn't have the resources to actually build a product like that.
But there were APUs in the desktop consumer market, right?
And there still are. I mean, these days it's common that there's a GPU. This actual vision of having like the GPU do lots of stuff, it slowly comes to pass now. Yeah, so the thing is that the thought is that an APU has GPU and CPU cores combined, same chip. Many core processors are just very many small CPU cores. So you're kind of like, you're still you have a core that's a bit of a mix of in the design space, somewhere in between a CPU and a GPU core. But a many core chip is homogeneous, whereas an APU has two different kind of units in there. Okay, more questions. Well, in the desktop and the notebook space, no, they just use LPDDR. In the HPC market, for sure, because in the HPC market, nothing you cannot get around HBM just because it has so much more bandwidth. The two chips here on the very left, those two chips use GDDR, and I mean you can see that they only do something like 700 gigabyte per second. I think the fastest GPU, the RTX 480, 4080, I think is around a terabyte with GDDR memory. But that is the same that HBM GPUs had 5 years, 6 years, 7 years ago, or something like that. So HBM is just so much faster, and that's why there's no alternative for HPC. Expensive though, which doesn't matter for HPC GPUs.
Question in the chat. How does L2 cache work for APUs? Specifically, is it shared between CPU and GPU cores?
Yeah, no, it's not. At least today. I know that for Intel in their integrated GPUs, they used to have a shared level 3 cache, but even that isn't shared in today's consumer desktop GPUs. For the MI300, we don't have a shared level 2 cache, so that those are still, because level 2 cache for a CPU is a very core private thing. Each core has its own level 2 cache, and so very close to the core. But they have a shared, well, what level would you call it? Somewhat difficult because they all have their own level 2, and then the CPU also has its own level 3, which is still private because it's on the die. You can actually kind of see it in between here that there's a level 3 cache. For the GPUs, they call it the infinity cache. So, or last level cache, and that's shared for the MI300, which is also kind of nice or kind of exciting because that also speeds up the data exchange between CPUs and GPUs quite a bit. And also it's I don't actually know the exact size of the cache. But should be in the hundreds of megabytes. So that will be kind of nice. For the NVIDIA, or for Grace Hopper, there's no shared cache at all, just because it's two distinct chips.
But it is cache coherent, right?
Yes, but I think you can opt out because it's often slower.
Yeah, that will be my question. How do they manage that? I mean, these are incredible speeds and really low latencies. And to keep that.
So I think if you read from the CPU, from the Grace CPU into GPU memory, you go via the level 2 cache. So that kind of enforces the level 2 cache coherency. And the other way around, probably 2. Yeah, probably 2. I'm not 100% sure. But usually for these kind of things, there's opt-outs because it's slower.